Question 3. This question is about phosphoric 5 acid. Part A. The phosphoric 5 acid is made in two-step process from the phosphorus. Step 1. Phosphorus react with excess oxygen to form a white solid. Step 2. The white solid then react with water to form the H3PO4. So therefore the equation is quite easy. So phosphorus, normally we will put the P4, right? One molecules of the phosphorus, it has 4 atoms in there. So P4 plus 5O2 form P4O10. Some of you might think the P2O5, but P4O10 is more stable. So normally we put P4O10. And of course, step 2 is the white solid, which is the phosphorus oxide, reacts with the water and is formed one acid, that is H3PO4. So you just balance it accordingly. For part 2, H3PO4 is the weak Bronsted Rory acid. Then you need to know what is the acid about. For the Bronsted Rory acid, we know that it's always a proton donor. Means it will donate one proton out and others will gain the protons. I give one example with this H3PO4. H3PO4, when it reacts with water, so it will release one proton and it will form this H2PO4 negative. And the protons that release, it will gains by the H2O, and the H2O now will form the hydronium ion. Okay, so we know that the H3PO4 now is a proton donor because it's lost one proton, and therefore is acid. And the water now is a proton acceptor, is a base. And the H2PO4 negative that form is the conjugate base of this acid, the H3PO4. So they are one pair, right? So conjugate acid-base pair. Now part 2, define weak Bronsted Rory acid. So it's quite easy. The species that donates proton. Okay, weak acid means is partially dissociate, okay, in the solution. Part B. H3PO4 is also formed in the process shown in this reaction 1. It's from the H3PO3 and it will form the acid and the PH3. And table 3.1 give some enthalpy change of formations for these products and reactant. Okay, later we're going to use this for the calculation. Okay, before that, let's go to this part 1. Define enthalpy change of formation. Okay, I give you one examples here. Enthalpy change when 1 mole of a compound is formed. Let's say now we have this oxide, this iron 3 oxide. So must be 1 mole, and this compound, it must form from its constituent elements, means this iron and the oxygen. So it must be the elements, it cannot be the compound. So for the iron and oxygens, they are all elements, and these elements, it must in their standard state. Means under standard condition 25 degrees C and 1 atm. So this iron is solid, oxygen is gas, and it will form this iron oxide, which is solid. So this means standard state, means the state, okay, under the standard condition. Okay, so this is definition. And part 2, use the data in table 3.1 to calculate the enthalpy change of reaction for this reaction 1. This is a reaction 1, I already put it here. So we know that to get the delta H of reaction, we need to use the sum of the formations of products, okay, minus the sum of the delta H formation of reactants. So means the products now is the H3PO4 and PH3. So we use these two products minus this reactant H3PO3. So therefore now we need to substitute the value. So because here is 3 moles of H3PO4, so we use 3 times negative 1281, okay, plus the formation of this PH3, so it's 9, okay, minus 4 times of the formations of this H3PO3, which is negative 972. Okay, so at the end we'll get positive 54 kilojoule per mole. Part 3. Explain why reaction 1, okay, this reaction, is a disproportionation reaction. Explain your reasoning with reference to the oxidation numbers. In this reaction 1, the elements that we need to focus or we need to use is this phosphorus. Okay, so we just use phosphorus and see what is the change in its oxidation states. Okay, before the reaction, the oxidation state of phosphorus is positive 3. Oxygen is negative 2 times 3, so it's negative 6. Hydrogen is positive 1 times 3, positive 3. So therefore, phosphorus is positive 3. And after reaction, the oxidation state of phosphorus is increased and decreased simultaneously. In the H3PO4, the phosphorus is positive 5. In PH3, because hydrogen is positive 3 here, positive 1 times 3, so therefore phosphorus now need to be negative 3. So means from positive 3 to positive 5, so this is oxidized. From positive 3 to negative 3, this is reduced. So we know that phosphorus now is undergo the oxidation and reductions at the same time. Okay, so this is the statement you need to give. Phosphorus in this H3PO3 is both oxidized and reduced simultaneously, and you need to state the change. So phosphorus is oxidized from positive 3 to positive 5, and it reduced from positive 3 to negative 3. That's what you need to give. For part C, figure 3.1 shows reaction scheme that involve H3PO4. Let's start from this one, this propene. So from this propene is formed this propane 2O. So we know that is addition reaction. So means it's going to add H2O, is a hydration, and hydrogen will add to this CH2, OH will add to this CH. Means this carbon. So therefore it will form this alcohol. And we know that H3PO4 here is actually a catalyst, and it must involve the actual reactant. So this A, it must be steam. So steam together with this H3PO4, and therefore it will undergo hydration to form this alcohol. And after that, this alcohol will form B, and this alcohol reacts with this mixture. This mixture is telling us the HBr will form, because when KBr and this acid that reacts, the HBr will form. And of course this salt we no need to really know, it's okay. The key is when this KBr with this phosphoric acid that reacts, it will form HBr. And the HBr, once it's formed, it will use to substitute the OH in the alcohol. So this OH being substituted by bromine. So therefore, it will form 2-bromopropane. Okay, which is this one. And of course, this alcohol will undergo oxidation here. So oxidation is happen when this H and this one actually this carbon has another hydrogen bonded to it. So these hydrogens will removed, okay, together with this hydrogen, and of course with the oxygen to form H2O. And eventually this organic compound, it will form oxidized and will form ketone. It will form this propanol. And for the reaction 3, the alcohol here will react with this ethanoic acid, okay, with the help of this phosphoric acid to form this ester. So this is the acidification. Type of reaction is condensation. Okay, so this is the whole reactions about. It's all start from this propene, and is helped by this H3PO4. Okay, now let's start part 1. Identify A. A already told you is must be steam, right? Part 2. Draw the structure of B. Already told you OH will undergo substitution and is substituted by bromine, right? So therefore it will form this one, 2-bromopropane. Part 3. Name the type of reactions that occur in reaction 3. Reaction 3 again is this condensation or the acidification. So is to let you to understand better. So please refer to this equation. So this is the carboxylic acid, and this is alcohol that used. So they will undergo condensation, and this one, they will combine the OH and H and form H2O. And the CO bond will form, means the ester bonds form, and it will form this ester. So it will form CH3COO, CH, okay, bracket CH3, 2. Okay, so therefore, now for part 3, name the type of reaction. It's very easy. Whenever it's type, we will say this one as condensation. So just give the answer as condensation, because this is one of the type of reaction in your syllabus. Okay, now part 4. This is an IR question. Reaction 3 is monitored using the infrared spectroscopy. It is not possible to use OH absorption frequency to monitor the reaction. Means it's telling you don't use the change in these two, means the carboxylic acid and the OH. So we not going to consider the OH here, okay, and what we need to look at is the change in this carboxyl group. Carboxyl means the COOH, and this carboxyl after reaction is formed ester. So it will change from this to these numbers. So just refer to the table. So when there is a CO double bond, the carboxyl, okay, its characteristic infrared absorption is this one. After reaction, I already told you, is formed ester here. So the ester now absorption change. So it's changed to this one. Means before reaction is 1670, okay, to 1740. Now is changed to this one, 1710 to 1750. Okay, this is the change that you must mention. Okay, I hope you understand. So therefore, your answer should be the CO double bond. Okay, the change in the infrared spectrum is absorption range now change from these values to these values, right? From the carboxyl to ester. Part D. H3PO4 also reacts with alcohol to form organophosphate. So this is the organophosphate. And this organophosphate has the 3 alkyl groups with it. Before you try to answer this, actually, at least you should know the phosphoric acid is looks like this. The structure is this. So means when the phosphoric acids reacts with alcohol, let's say the R group, it depends. So it can be methyl, ethyl, okay, and others. So let's say now the phosphoric acid reacts with one of alcohol with this R group. So the hydrogen will substitute by the R group, the alkyl group, and form this organophosphate based on this question. Okay, so this one, this H from the phosphoric acid, okay, and the OH here will form the H2O here, and this R will bond to this O, and this O, these 3 oxygen, right, and form this organophosphate. Okay, so this is how that looks like. If let's say the methanol used, if methanol being used means now the R group is the CH3. So the organophosphate that form is this one, right? So if you understand what I state, then you will know how to form this equation. Part 1, complete the equation to suggest the products of the reaction of H3PO4 with methanol. Okay, with methanol, H3PO4 with methanol. So we know that is from this product, right? And this product, the phosphorus is bonded to OCH3, OCH3, OCH3. So therefore, the formula you just give this CH3O bracket 3 and PO, this one, PO, plus 3H2O. Okay, because the hydrogens here is being substituted, 3 of the hydrogen here being substituted, and 3OH here being used, right, to form this 3H2O. Okay, compound T is a simple organophosphate. Okay, the mass spectrum of T show the molecular ion at M/E182, and this peak has the relative intensity 12.7, and the M+1 has relative intensity 0.84. Therefore, we can use this relative intensity for this M and M+1, right, to calculate the carbon number. So the carbon number, okay, we can use this one, right, to calculate. Hundreds over 1.1, and this one is the ratio between the C13, okay, to the C12, okay, times the relative abundance of the M+1 over the relative abundance of M. So we just substitute the values in there, 0.8 over 12.7. Okay, after that we'll get 6 carbon. If 6 carbon, then we know that if we refer back to this structure, the only place that has carbon is this, and this, right? If it's 6 carbon means the R group each must have 2 carbon, 2 carbon, 2 carbon. If it's 2 carbon means it must be ethyl, means it should look like this one. So means now the groups here is CH3, CH2O, same, and this one same. And therefore, you can give the molecular formula now. Okay, we start from C. C is, of course, C6. Okay, hydrogen is 15 because 5 plus 5 plus 5. Oxygen is 4, P is 1. So this is the molecular formula, right? Okay, that's all. Thank you.